some shit about it. So I really want to talk about the controller of the train, like the high level supervision state machine. So it supervises the system and reads some inputs and says what state that the machine is in. So as a simple example, as a simple example of a controller, we say we start in the off state. You can't see my mouse cursor, can you? Oh, okay. So we start in the off state, and we say that the engines and the air conditioner for the train are off. And we have transitions into the idle state when we turn the power on. And when we're in the idle state, we have the engines are still off and the air conditioner is on. And finally, we can turn the ignition on and we go from the idle state to the driving state. And then we turn the engines on. And if at any point we turn the power off, then we go all the way back to the off state and make sure that the engines and the air conditioner are both off. Or if we just turn the ignition off, we go back to the idle state. And so the reason we write this as a high-level state machine like this is because even though our implementation is probably going to be pretty hairy, or hopefully not going to be too hairy, but it's going to be running probably C code on a microcontroller. We want to reason about it at a high level and be able to say, well, you know, there are only 3 states here and only 5 transitions, so we can't get it too wrong. Like we can think about it abstractly at this level and be relatively confident that it's correct. So so we might as well make it a little bit more interesting and say that we also have a failure mode. So there's another input. Suppose that the train has another input which says whether the temperature is outside of the good operating range, like it gets too hot. Say the self-driving train camera gets too hot to get videos out. So if the temperature goes bad while we're driving, then we want to go down to the failover state and leave the engines on because they're mission critical, but we want to turn the air conditioner off and any other kind of superfluous things, like any luxuries we want to get rid of. So we say, okay, if the temperature is bad, we go down to failover, or if we're in idle and the temperature is bad, we go back to off because we're turning the aircon off. And if we're in failover mode, and the power is off or the ignition goes off, then we go back into off mode. So I think hopefully that's like a high level enough state machine to say, yeah, this is the system and it's got the right fault behavior. Like if something goes wrong with this train running this system, then we know that it's going to fail in the right way that we want it to. So we've got our beautiful state machine. How do we actually implement it on the hardware? we've got an embedded system, so it's got to run on a microcontroller. There's limited space on these things. It's got to run not quite forever, but we don't want to worry about crashes and out of memory errors and things like that during runtime. And we also want to have like predictable scheduling runtime. So the time between iterations should be relatively similar. So given these constraints, what do we implement it in? Well, it's got to run on a microcontroller, so probably C. It's limited space, so probably C. If we don't use malloc, well, probably C. And we can get predictable runtime from C, which we can't necessarily get from a garbage collected language, right?
So Amos, can I just jump in there for a moment?
Yes, please do.
Why not cogent?
Yeah. Absolutely. Yes.
Not invented here is a valid response.
No. Cogent is, so I'm gonna just, I feel like Lustre and Cogent are in many ways duals to each other. So Lustre is all about data flow. It's a data flow synchronous streaming language. So it's all about how things change over time. Whereas Cogent is a control flow language. So it's about a bit more about data structures without loops in them. It's
no, so that's fine. That's
yeah.
Good explanation. I'm happy with that.
But yeah, definitely it's an option. So yeah, it looks like so coming from a typical systems engineering background, you would say C is our only choice because we can't use a high level language like Java or Haskell, right? And as much as I would love to use Rust, in this case, C has better tools for proving stuff about it than Rust does. So we can verify we need the verification tooling to be mature enough. So Rust is the other contender, I guess. But yeah. So it's sad. We have to write it in C. And it ends up, it's not too bad. It's only 50 lines or something, if that. But it's not great. So I have hold on. Okay. Can you see my mouse pointer now? Hopefully.
Yes. Yeah.
Excellent. So if you're in case off, you say, if the power is on, then we turn the air conditioner on and we go to the idle state. And for the most part, these states tend to fit with the system, but it's not great because it's not obvious. Whereas in the definition of in the graph, in this abstract state machine, we said whenever we're in the off state, our engines are off and our aircon is off. But if we look at the C code, we say we're in the off state and we move to idle and turn the aircon on. So you're just looking at the definition here of idle or of any of the states, we can't tell what the state of the machine is on. And that's one of the problems of C, and I don't think I really need to spend too much time convincing you of the other ones. So we've got this bad C code. We've got this beautiful, beautiful state machine that I drew, and it's pretty dense information, but it's abstract enough, right? So we want to retain this beauty. So we want something more beautiful, which is Lustre. So our Lustre program, Lustre is like a streaming language, but it's for embedded systems mainly. But our Lustre program, which implements this this state machine, has this type signature. So it says, I have a controller node called controller, and it takes as input the power and the ignition and the whether the temperature is bad, and they're all Booleans. And it returns whether the engines and the aircon should be on or not. So it's just it looks like a pure function from power and from a triple of bools to a pair of bools, but it's actually a pure function from a stream of 3 bools to a stream of 2 bools. So the power and the ignition and the temperature are all input streams, which are defined at every point in time. And the outputs here are output streams. So, so we can define that their state machine in Lustre like this. We say we've got an automaton and the initial state is off, and in the initial state, the engines and the aircon are both off. Then, if the power is on, we go to the idle state. And this is called an unless transition. It's called a strong or an unless transition because it happens before setting the engines and the aircon to false. So it happens, you enter this at the start of an iteration, you say, is the power on? Yes, go to idle. And now I'm in idle state and I use the outputs defined in the idle state. But other than that, it's almost like the state machine. I mean, it's a textual form of the same state machine. So where in the state machine, we said off goes to power, goes to idle when power is on. Here we say off if power, restart idle. So restart the idle state. And same in idle state, if the power is on, if the power is off or the temperature is bad, we go back to the off state. So you could easily draw the original state machine from this, I believe. So this is good because compared to the C, it's clear here that the engines and the aircon are always on when we're in driving mode. We don't have the issue with the mutating the mutable variables, really, where when we change a state, we're describing the state of the world that we are at now, rather than the changes we want to enact on the world to make it in the state we want. And that's, I think, very important for making it obviously correct, right? And it also has a benefit over the diagram, because where the diagram was a bit ambiguous, because it said, go back to the diagram. Diagram has 3 output transitions here: not ignition, not power, and temp bad. And they're all 3 of these could be true at the same time. So we haven't specified the precedence here. So writing it down in a textual notation has forced us to document that, to remove that ambiguity. So we have our beautiful state machine in Lustre. And now what we want to do with it is verify that it means something good. Like, so we're going to verify it, and then we want to later compile it to C and then integrate the generated C code with the rest of the system. But first we want to verify that the state machine itself actually means something good, that it's a valid state machine. So looking at this state machine with the failure recovery, one property that I can think of is that, well, if we look at this, we go from the driving state and the temperature is bad, then we turn the air conditioner off. And it's similarly true here. If we're in the idle state and the temperature is bad, then we turn the aircon off. So I would hope that in our in this state machine, it seems like whenever the temperature is bad, the air conditioner should be off, because we don't want to be wasting precious electricity and generating heat when it's unnecessary or when it's detrimental. So we want that property. So let's see. Yes. Okay. Is that big enough? Cool. So to describe that property, that you write, this is a property, and then we say temp bad implies not aircon. So if the temperature is bad, then aircon is off. So we write that property inside the state machine and use kind2. Kind2 is the verification tool for Lustre that we are using. So kind2 controller.lus, and it will oh no, it says temp bad implies not aircon is invalid. So if I make this bigger, it tells us, the property that we wanted to prove about our thing is not true. And here's a counterexample that it gives us. So it says if you start in the off state and then the power is true, the ignition is false, and the temperature is bad, then it's going to be, then the aircon is going to be true, and the state is also going to become idle. So if I go back to this, it's saying that we start in the off state, and then the power is true, and the temperature is bad. But there's no, so if the power is true, it's going to go into the idle state and go here and turn the aircon on. So it is a genuine mistake in the state machine that we probably should not be going into idle mode if the temperature is bad, even if someone requests to turn the power on. So we should probably change this to power and not temp bad. Right? So we can change that in our implementation here as well. We say in the initial state, unless if power go to idle state, we say if power and not temp bad go to idle state. Now, if we rerun the model checker kind 2, it says, yes, it's valid. So what this has actually done is managed to construct a proof that for all possible executions of this state machine of any possible length, there's no way for the temperature to be bad and for the air conditioner to be on. So we could just test it by going to the failover state, which is the one it goes to when the temperature is bad, and saying, well, what happens if we make the air conditioner on there? So that should make our property fail, right? And it does. It says, well, if you start and you turn the power on and then you go into driving and then the temperature goes bad, it'll get to failover and the aircon will be on still. So it's able to so by writing down the state machine in Lustre, we can also write down the properties that we want to be true for the state machine and have the machine check them and the machine prove them for us or find counterexamples. So that would be, I would say, a massive benefit of this, even if we couldn't. Like that's a reason to use it alone, I would say. A reason to take your C code and write a model of it in Lustre and check whether the C code is correct. But even more than that, we can take the Lustre code and compile it to C. So we can generate some C code, and and the C code is pretty funky because it has these, it's not that bad. But where we wrote the manually written C before, we just have to call the step function for the state machine. So the Lustre node takes the power and the ignition and the temperature, whether the temperature is bad, and returns the engines and the aircon. That generates two functions. This reset one, which just initializes memory. It's just setting it to the initial state. And then it also has this step function. And the step function takes the power, the ignition, and whether the temperature is bad, as well as an output struct, a pointer to an output struct, which is what to fill, where to put its results in. And this memory struct describes the internal state, which is like what state the state machine is currently at. So then
I was going to say, like, sorry, I was going to say, like, the C code is pleasantly well formatted. So just like a little side comment there.
No, this is my stuff that I wrote. This is the code that I wrote to call the generated C code. I'll show you the generated C code. So this is.
I was actually just complimenting you.
So this is the API that it generates, the header file. So the step function, yep. And then the implementation is pretty funky.
Right. That is really funky. I see that now. Okay.
So they don't make these compilers to be fast. They don't make them, they don't really optimize for generating good code. They optimize for predictable code, so that it always takes the same amount of time, no matter what you call it with.
Yeah, I guess that makes sense though, because like just thinking about it as from an operational perspective, unless you have like really strongly defined like time constraints, you just learn how to deal with however long it takes, but you want that to be reliable.
Yep, exactly. Yeah, so it's and it never really helps if you can it only helps if you can make the slowest execution faster, because increasing the common case or making the common case faster doesn't help if you've got a case that only happens every so often, but it takes 10 times as long, because that's how much time you've got to allocate for it. So you're only really interested in the worst case execution time.
Right.
But yeah, so it's a bit funky. It's idiosyncratic. But I don't know. I can't say much about it. It's not good, but I'd rather have someone else generate that than me have to write the original C code.
So how does this compare to the sort of C code that I would have written when I was writing state machines in C code, where you write a transition function, a generic transition function, a generic output function, and then parameterize them with a transition table and an output table?
Right.
And I mean, if you wrapped your two if statements here into a function that was driven by a table, an output table that took a state and returned and performed the appropriate on or off function set calls, you would have something that was very similar to what I would have written by hand. Only instead of being driven by a very large case statement, it would have been driven by a couple of two-dimensional arrays, a couple of big tables, often pretty printed with the help of the C preprocessor.
So I guess I've really only shown you the state machine part of Lustre, and it's got quite a bit more power to it in terms of the streaming model. So
okay, yep.
So
once you start talking about the dynamic behavior of the system with changes, then it becomes more. You still have the same proof ability.
Yeah. So I think this is in some ways more expressive than more expressive than the tables themselves, without having to go out, shell out to sea proper. And so it's more expressive than the tables, but it's still less expressive than C itself. So you
want it to be, you want to be able to prove things.
Exactly. Yeah. So it's still quite limited in terms of it's really only finite state or bounded state things, and a constant amount of computation on each transition, but those both help you prove, mean that the automated tools can prove a lot more about it for you.
Cool. Okay, thanks.
Yeah. Yeah, so you write these state machines in Lustre, you prove properties about them, and then you write this manual C code to really to plumb the inputs in from the outside world. And then the Lustre machine gives some output that says what commands it wants to enact on the outside world. And you need to plumb that in. But yeah, that way you can at least prove that your understanding of the state machine matches a lot more closely to our original diagram. So I think it's apparently Airbus, the French plane company, they use this quite a lot, the Lustre stuff. And yeah, I think it is used in trains and things like that. But so at the moment we're using it in microcontrollers for we've got this thing called which is really the controller, the supervisor that makes sure everything is in the right state. And we use it for both the high level supervisor state machine, because that's it's actually not that much more complicated than this, but even this, it's easy to overlook something, right? Even at this level of complexity. So it helps there. And we're using it with the implementation of each part. So actually getting the temperature in order to tell whether it's bad has to go through a few different stages of hardware, a few different pieces of hardware need to talk to each other correctly, and there's different states that they can be. So there are a few state machines there about resetting and other things that we want to make sure are correct. So we're using it there as well. And it seems, I certainly think it's a lot better than writing C code. And I think even if Rust had, like, I would like to be writing Rust code for the stuff that doesn't have to be C. sorry, for the stuff that doesn't have to be Lustre. But given that even if I had verification tools for Rust, I think that this would still be useful because we could still prove more things more easily about it. So yeah, it's just it's a shame that it doesn't have some types, but that's the main thing I feel is missing. Yeah, anyway, that's all I have to say about Lustre today.
Cogent's support for some types.
Sorry?
How is Cogent's support for some types?
Oh, very good.
Okay.
Very good in terms of the yeah, it supports them very well. It uses this this nominal structural system, so you can upcast if you've got an A or a B, very similar to the polymorphic variants almost. If you've got an A or a B, and you've got another type which is A or B or C, you can promote A or B into an A or B or C. It's interesting. But,
I'm loving how we managed to sync up.
yeah.
Unintentionally, but it's great.
It's funny.
Have you ever used it for network protocols where you might have messages queued up on the network and so that they become part of your state that you need to model?
I haven't yet, no. So I'm not sure about, yeah, I guess one thing I glossed over is that all the variables that you have need to be statically fixed size. So any arrays that you're dealing with need to be exactly X bytes or whatever, exactly X elements. So as a result, it's not so great for dealing with data, dealing with pulling data out. I'm not sure how it would go for network protocols, but it'd be interesting to try.
So how does Lustre deal with that? Like, does it type check that, you know, your vectors are of certain size all the time, or can you write, or do you need to write properties so that you know that you're not like overflowing some buffers or something like that?
The type checking occurs in the size. Type checking happens for constructing the vectors to make sure that they're all exactly fixed size. Like the type of an array is X int 8 or something. There is no array of unknown size type. There always has to be a number after the array.
Right. And if you try to access like the position like 9 of that, will Lustre just refuse to compile?
So for indexing, I think there are two kinds of indexing. There's weird. You've got an array, take X, and there's also normal array X. And one of them is checked at compile time by the property, the proof checker. So it's not a type checking check. The other one is checked at runtime, I believe. And
right. So depending on, I guess, like your situation, you might get the benefits of compile time checks, but you potentially would also want to write some property tests, right?
Yeah. So
Right.
so these are, they're not quite property tests though, right? So this.
All right. Well, so you, yeah.
So it's not. While a property test uses random data generation, this is what this is actually doing is generating and converting it to an SMT formula and sending it at an SMT solver that can prove whether it's whether this property is satisfiable. But, yeah.
For this example, could you use something like small check and just exhaustively search the possible state transitions?
Yeah, actually, yeah, because the only state here is which state it's in, which isn't very interesting. So, so I thought something that I thought would make this more interesting or more realistic would be if when you're in the failover state, you do want to be able to get back to the driving state, right? But you want to be very certain that the temperature has gone good again for good. So what you could say here is say something like num good is, so I'm imagining like you want to count the number of times that the temperature has not been bad, and if it's greater than 10 or something, if you say yes, it's not bad for 10 times, I can safely go back to driving now. So you could write something like num good is if temp bad then 0, else the previous value of num good plus 1. So the previous value here is the value at the previous iteration or the previous state. So I'm imagining that you could also say else if num good greater than 10, then restart driving. So in that case, it makes the state space a bit more interesting, right? You're no longer dealing with, I mean, it is technically a finite state machine still, but it's got a little bit more state in it. And when you start adding this sort of stuff, it's going to become more difficult for something like small check to exhaustively test the space.
Yeah, okay.
Yeah, cool. Well, I think that's all I have to say.
Anyone got questions?
No? Cool.
Well, thanks, Amos.
Thank you.
That was really interesting.
Amos.
Thanks, Amos.
Hi, Matt.
Hello, it's been a while.
Yeah, how are you?
Yeah, not too bad. Yes, verifying things, but or failing to verify things, as the case may be.
Failing to verify them because they're false, or failing to verify them?
I guess because we have no idea what we're doing.
Yeah.
Yeah.
That's less.
That actually sounds like talk.
Well, I'll get back to you in a few months when I'm possibly. Sorry, what? We're currently trying to port, Thomas's binary verification stuff to the RISC-V. To the RISC-V port of SEO4, and I mean, Tom's really smart, and none of us understand anything he's done. So,
Yeah, that kind of sucks.
yeah.
Oh, I'm going to call it a night. An early FP-SYD for me.
Need the microphone closer.
So you don't understand that? Do you not understand me waving my hand like that?
You just want your team to speak.
All right, everyone. Thanks, Tim, for setting this up. And yeah, it's nice to speak with everyone. This isolation's been rough. So, nice to see you all. Nice to see everyone again.
Yeah, thanks everyone for turning up and that. It's been great. So we'll run. Since we don't have to put chairs away at Atlassian, then people can stand around and talk if they want to. But yeah, we'll run again same time or same last week or whatever it is. 27th, I think it is. We've got Hugh and Barry, so I'll try and get in touch with them and tee them up for talks for next month. If anyone wants to do a lightning talk or anything like that, get in touch and we'll slot you in. We also have some empty speaker slots towards the end of the year into like August, September, October. So if someone wants to speak but doesn't want to speak quite so early in the year and needs a bit more time to prep whatever they're doing,